My name is Tom Parker, and I'm the Director of Security Consulting Services for Securicon. We're a small boutique practice right outside of DC. Do a lot of work with the federal government, who have a diverse set of requirements and so forth. And so attribution is a topic which is very near and dear to me and a lot of the people that I do work with on a daily basis. Today we're going to be talking about attribution as a high-level topic, in addition to delving into some of the intricacies of how we might be able to achieve attribution, some of what's been done in the past, some of the limitations with the tool set that we currently have today. Greg Hogland did a great talk earlier today on malware analysis, and we're going to look at some of the concepts that he put forward in a bit of a broader purview to try and rate an attack and a piece of malware and some other components associated with attacks, using some existing methodologies for analysis and some new technologies which I've conceived over the last couple of months. There will be a tool release in accompanying this presentation, which I'll provide you all a link for. One final note: these slides have changed slightly from what you have on your CDs. So I was thinking that we still had those big, thick books that you could use for doorstops at Blackhat, but I guess they've stopped giving those out now. So. But if you do have the CD up at the presentation on a laptop, it will deviate slightly from what I'm about to show you. So attribution is really become a top-of-mind topic over the last couple of years, specifically because the media has started paying a lot more attention to purported nation-state-sponsored efforts, organized crime, various botnets, which have gleaned a lot of media attention. The Wall Street Journal, about 16 to 18 months ago now, published a talk entitled Wide Cyber Attacks Linked to China, which is very speculative in nature, and what it basically said was that the Chinese are responsible for all kinds of badness against the defense industrial base, or DIB as we call it in DC, which is basically a term for the big contractors that do a lot of the work for the Defense Department and intelligence communities. 60 Minutes had a piece probably about 12 months ago now called Sabotaging the Systems, where they were talking about control systems. Again, there were a lot of inferences around that regarding what could possibly have been state-sponsored attacks. The Google Aurora incident, is there anyone in this room who hasn't heard of the Aurora attacks? Okay, good. Well, the media is doing its job, I guess. Aurora was, a huge incident, got lots of publicity, lots of speculation concerning who it may have been, whether it was the Chinese or perhaps a smaller group of individuals. And then most recently, there's been a lot of press around the SCADA malware that's been given the name Stuxnet, which targeted Siemens SCADA systems, specifically an HMI component. And again, there's been a lot of speculation around that and whether it was potentially state-sponsored. There's been a lot of infections in Iran and other countries in the Middle East, so there's even been some speculation that it may have been us that created that. So we're actually going to look closely at Stuxnet later on and use some of the characterization matrices against Stuxnet to try and determine a little more about Stuxnet as a piece of code rather than just the functionality that's immediately obvious. So one of the big problems that we face in the cybersecurity community, it's not just information warfare that faces this, is a lack of a common lexicon. This is especially an issue if you look at the technical communities and the defense communities. Everyone seems to use similar language to describe different things, and there's a very similar problem in the information warfare space. Of most note, the word cyber war means a lot of different things to different people. I like to take the approach that if you take a look at what cyber war really means from a literal standpoint, an act of war is a legal state between two nation states. So it's not really a term that people should use lightly. I know what they mean. They mean cyber warfare as a tactic. But if you see an article entitled "War Between the US in another country, that invokes a lot of thought in terms of other potential side effects of that, so maybe even a kinetic war that might accompany it. So in a lot of the working groups that I'm a member of, we like to call it cyber conflict to describe the more peacetime but clandestine operations that we think various countries may be involved with against each other. In this talk, when we talk about an adversary or an actor or attribution, what we're going to be talking about is not necessarily finding an individual's home address, what they eat for dinner, when they go to sleep, but we're also going to be talking about attribution on the level of the state level, so state-sponsored capabilities, as opposed to individuals within maybe a state-sponsored unit. We're going to look in a minute about some of the reasons that we don't really often care about the individuals behind the attack. And finally, since it's all over the press, I wanted to mention APT, or Advanced Persistent Threat, or Average Persistent Threat, as some of my colleagues jokingly call it. To different people, APT means different things. I've heard 1,000 different explanations for what an APT is. It's certainly not a term I'm going to be using now, and I would encourage anyone that has a technical conversation with anyone about advanced persistent threats to ask them what they really mean by that, to talk about specifics rather than just using acronyms, which are often used as marketing tools these days in our industry. Okay, can anyone tell me what that is? While I get myself some water. No? There you go. Yeah, that's a, So this is a high magnification on some ballistics evidence from a fired bullet, and this is the same thing, looking at the back of where the firing pin is hit. And the point of these slides is really to demonstrate that a lot of the technologies that we have today just tell us, or are akin to telling us that the guy was shot. Well, great. What kind of gun was he shot with? Where was it manufactured? Maybe we can figure out what the serial number of that weapon was. There's a lot of information that we could be deriving from a lot of the attack analysis data that is available to us today, but we're really not taking full advantage of. And there's a lot of research in the forensic space for profiling and characterizing common criminals in the kinetic world, but we really don't have that body of research in the cyberspace right now. So why do we care about attribution? First and foremost, and perhaps most obviously, as a law enforcement tool and as a deterrent. It's a fact that the more people that get caught for crimes, the less people that are inclined to commit them. Obviously, the law enforcement community in cyber investigations rely heavily on the ability to attribute attacks to individuals for purposes of catching the person that did it. But perhaps most importantly, in terms of actor intelligence, as a tool for any kind of investigative organization, whether it be the intelligence community, whether you're a large bank, being able to attribute the attacks that are being targeted against your systems, or at least building up a knowledge base on what's important about those attacks, is very important in terms of profiling our adversaries' capabilities and how we might be able to develop countermeasures to address those. It's also very important to be able to create linkage between actor groups, and I think Greg was perhaps talking about this a little bit earlier on. But being able to say that, okay, 12 months ago we saw this attack over here, it attacked this system, it used an agent rootkit that we haven't seen anywhere else, we don't believe it's commercially available for sale, and then saying, well, 12 months later we saw this attack over here and we think that it's probably state-sponsored because of these other attributes, and they use the same technology. It's very important to be able to create that linkage between the two incidents, and therefore potentially track the supply chain through which the adversaries in the latter attack were able to acquire that technology. So to step back and talk about the point that I touched on earlier, what are we looking for when we talk about attribution? Well, the obvious is an individual that kicked off an attack, who they are, where they live, their geographical presence, what their motive was behind the attack, what their capabilities are, but we're not necessarily just looking at that. We're also interested in actor-level groups in terms of what the high-level capabilities are of a nation-state organization, the budget that they might invest in certain capabilities, and so because of that, people think attribution and they think, oh, well, it's really difficult to find exactly who that person was. A lot of the time, you don't necessarily care, because having that higher level of information about the people that you're dealing with or groups of people that you're dealing with is often all you really need to develop those countermeasures. So again, one of the things we're looking to do here is to differentiate between different actor groups, identify groups by their geographical presence, any indications of sponsorship that we might be able to attribute, such as whether it was an attack from China versus Russia versus Korea. If it was the work of an activist group, you don't really hear a lot about this in the press anymore, but if you go back 5 or 6 years, you see a lot of cyber attacks that were mounted by people like the Animal Liberation Front, the Environmental Liberation Front, have been surprisingly active in this space. These days, all we're talking about is China, Russia, and people with Islamic persuasions that want to use the internet to attack our infrastructure. But there's a lot of activist groups as well that have also used cyber capabilities in the past. And again, identifying where worlds collide, identifying where two groups have shared a similar piece of code. Maybe they're colluding together on a project. Maybe those groups have joined together. There's various cases where hacker groups on the Asia-Pacific Rim have joined together to form teams and more formidable actor groups. So there's a number of conventional means that we use today, and some of you are probably very familiar with a lot of these methodologies. Static binary runtime analysis, either where we're looking at a binary without running it through a tool like IDA, or through runtime analysis using a tool again like IDA, OllyDBG, WinDBG, or any of the commercially available tools. Memory forensics, using tools like Mandiant's Memorize, has become a lot more popular recently, especially with the proliferation of rootkits adopted within malware. Tools like Memorize that can look at the physical memory for inconsistencies in what the operating system is reporting versus what's actually there have become a very important part of the analyst toolkit. Being able to look at the vulnerability itself and the payload is a technique which is very commonly used today for purposes of developing IDS signatures. But a lot of those methods can also be used to help us with attribution, and we're going to be looking in detail in about half an hour about what attributes associated with the exploit and payloads we can really leverage to tell us a lot more about the adversary. Command and control is obviously something that a lot of people look at these days. The first thing that an analyst will typically do when they're running up a piece of malware in a sandbox is they'll look at where it's talking to and then try and establish what the architecture is. Command and control architectures are generally heavily tiered. That was random. And contain lots of different hosts. So if we can track command and control channels, that often helps us provide more information about the geographical location of the adversary. And again, post-exploitation forensics is very commonly used these days to look at the file system and what tools have been dropped on the file system. But again, not really with a spin around solving the problem of who it was and what their capabilities are. So if you think about any forensics analysis tool, whether it be a sandbox-based runtime analysis environment or a disassembler or antivirus, generally all of these technologies are aimed at answering one of a few questions. What it was that happened, how did they get in, what exploit did they use, what was done once they were on there, are they still there, and how can we prevent this in the future? And there's a good reason for this, because there's a big market in being able to determine what all these things are, because if you're an incident response group, this is probably all of these things are probably going to be the first things that your management are going to want to know, so that we can reduce the impact of the attack and hopefully make sure it doesn't happen again. However, none of these things are really conducive to the attribution effort. Again, antivirus is mostly based off of known signatures today. There are various technologies, such as Symantec's Bloodhound technology, which try and look for virus-like characteristics. But if you talk to any VXer worth their salts, they'll tell you that all of these mechanisms are pretty trivial to circumvent. And again, sandbox runtime analysis environments we've already mentioned are really focused around answering the question of what the code does. So there's clearly a lot of R&D associated with modern antivirus and analysis technologies. Most of these technologies are designed to give us a 1 or a 0 in terms of telling us, is this bad or isn't it? Specifically in the case of antivirus. If you look at a lot of sandbox-based utilities, they'll tell us what the code does, but they don't really tell us how they achieve that, or provide any mechanism or insight into the merits or demerits of how the code's been implemented. And there's a lot of, and therefore there's a lot of metadata that gets processed by many of these tools under the hood, but none of that data is really exposed to the end user, so we can make good use of it for attribution efforts. And because of that, there's a real need to either adapt the existing tool set, or build new tools which are more geared around the attribution question. So, changing gears for a second, attribution is a topic which I've been studying with a bunch of folks around the Beltway in DC for probably about 9 or 10 years now. And we've had a bunch of working groups with members from 3-letter agencies, large organizations like Microsoft, to really try and answer the question of how can we start building data models around characterizing the adversary, not necessarily the problem of attribution head-on, but how do we start describing a set of adversarial traits. And so this is one of the models that we came up with, where you have basically 3 major properties that we try and analyze. You've got the environment, and that's the environment that surrounds all of us, around the target, around the attacker, and 2 really important relationships, and that's the motivation and the capability between the attacker and the target. And without a motivation and with capability, there's not really a threat to your systems. With capability and no motivation, again, there's not really any threat to your system. So one of the things that we try to use this model for is what variables are required in this model based on who your organization is to really consider an attacker to be a threat to your systems. And what we're not looking at here is a low-end adversary. What we're really looking at is, okay, we've got a generic security posture, we've put all these things in place, we've got IDSs, we've got IPSs, we've got all the snake oil that the security industry can throw at us. Now we're worried about the guys that are really going to break into our network, that are serious players and going to break into our systems. How are they going to break in? And what are their variables going to look like? So one of the things that we try and observe is the inhibitors associated with an attack. So what thought process does an attacker go through before launching any attack? What's the payoff given success? What's their perceived probability of success? What's going to happen to them if they're attributed and detected? And what do we think their uncertainty regarding the parameters of the attack will be? And of course, another thing that we're looking at, given each information system that we might be considering, is what's motivating them to attack this system in the first place. Are they trying to steal source code? Do we think they're trying to steal social security numbers? What is it that's really driving them to execute the attack in the first place? Obviously, the probability of success is often a major motivator for a lot of attackers. If someone thinks that they're highly likely to break into a system, they're more likely to want to execute that attack. And again, what are the perceived consequences of failure? It's a bit of an odd one, which you don't normally think about, but a lot of the studies we've shown, especially with a lot of the folks that I've spoken to that deal with a lot of the issues in the Asia-Pacific Rim, it's a very real consequence that someone may be recruited into a state-sponsored program and told that if you don't do this for your country, we're going to make sure that your family never works again. There may be physical intimidation. So that's another thing that you have to consider when looking at the mindset of why an attacker engages in an attack in the first place. And so this brings us on to being able to rate the attack based off of various metadata that we can observe. So again, this research that we're presenting now is about 5 years old, but I'm showing it to you just to give us a basis for the analysis that we're going to do in a few minutes. So we were looking at key attack metadata, such as the sources of attack. As a lot of you will know, the IP address of where an attack is coming from is of limited merit for high-end attacks these days. Other relevant packet data, such as the operating system that the adversary is using, may not be their own system, but if you talk to a lot of attackers, they'll tell you that the systems that they break into on the internet to act as bounce hosts will generally be operating systems that they're more comfortable using. No one wants to break into some old IRX box that doesn't have a compiler on it because it doesn't have a license, and that's no good to anyone. So the operating systems that are being used to attack systems are also of interest to us. And then what was the methodology behind the attack? Is there any observable planning that we could see that occurred? What was the score of the execution? And how was the follow-through? What was it that they did once they were in the system? And actually, on the point of planning, Dave Attell posted an interesting note to Daily Dave the other day, or maybe a few weeks ago, on just this point, that a lot of the high-end attacks that we see these days are so advanced that the only chance we often have to stop them is by identifying the attacks during the planning stages. So these three phases of the attack really are very important to analyze, so that we can, even if we did get hacked into, maybe we can now develop signatures so that we'll see the planning in the future. And once we've analyzed the methodology, this then brings us on to the individual attack tools that got leveraged during an attack. So every attack tool comes from somewhere. There's a lot of hard work that goes into writing exploits. Anyone that's written an exploit these days will tell you that there's a lot of late nights that get involved in, especially circumventing a lot of the modern mechanisms such as hardware DEP and ASLR. But you can split those into two primary categories, those which are public and those which only exist in the private domain. And one of the first things we might try and do with any attack is try and establish whether the tool exists publicly, or we think that it was something that the attacker developed themselves with the specific purpose of attacking our systems. And the major difference between these two subsets, if you look at a lot of attack tools, is that the public exploits which exist out there generally are only designed to prove a concept. So someone's written it just to prove that this really is a real vulnerability. A lot of the time vendors won't pay any attention to you unless you develop some kind of proof of concept to show that it can pop a shell under certain environments. And because of that, they're often not very reliable in terms of attacking a diverse set of targets. So you'll find that, for example, MSRPC overflow may only work on a very specific version of Vista with a certain service pack and maybe language pack installed. Whereas those which exist privately are generally a lot better written. People have a tendency to invest a lot more time in things that aren't going to be shared openly on the internet. Are generally better written and are often based off of attack APIs which are private to the individual or group which they're working within. And by attack API, we're really talking about private versions of things like Metasploit, which facilitate in the exploit writing process, whether that be building shellcode or a system call proxy, and identifying potentially from the attack if we think a public API was used or if we think that they've grown something themselves. And in the case that we have access to the tool, either through it being public or through it being private and some other intelligence source, we'll then want to consider a number of things. So how easy was it for the adversary to use that attack tool? Was a lot of prior technical knowledge required to use the tool? Did they need a lot of information about the target host, or did it do self-enumeration of the remote service pack, operating system, and so forth, or was it more of a point-and-click kind of deal? And was it appropriate for a given task? You hear all these statistics about how many billion attacks the DoD receives every year and so forth, and the fact is a lot of those are automated attacks of some kind, and if you can take that population of attacks and filter out all of those which were stupid things like IIS exploits being fired against Apache servers and so forth, you're probably going to slim that sample size down significantly. and give you something more manageable to analyze. So as a progression of that, we then came up with these various attack matrices to analyze various types of exploits against systems. So this is just an example for web applications. Different organizations may weight these differently based on the types of assets you're trying to protect, but this gives you a basic example of how you might be able to automate creating a scoring matrix to rate an attack based on whether the exploit use was public or private, or at least whether the vulnerability being exploited was in the public domain or something homegrown. In the case of applications, was it a proprietary application that you've written yourselves, or is it something that the adversary can go and download from the internet? So it's clear that there's a large body of analysis research which exists within the public domain, which we can rely on to help develop our analysis tool set further. And as we mentioned previously, most of this is geared around traditional incident response. And in a lot of cases, it's just not appropriate for attribution. And there's a lot of people out there who are mostly in good faith trying to perform attribution using tools a lot of the time which really aren't appropriate, and drawing conclusions which aren't necessarily accurate, or at very least they may be accurate, but they really don't have any technical backing to substantiate the research. So there's a clear need for reduction in the guesswork. We need to make the topic of attribution more of a science and less of an art form. We need people speculating less and relying more on substantiated information which we can build a body of research on as a security community. And we need common attribution models that different organizations and different researchers can use to communicate information about attackers, about attacks, and about attack patterns to each other, so that we're all playing from the same sheet. So I just wanted to mention a couple of technologies which have started doing this already. And there's clearly a lot of science behind profiling of criminals. Behavioral science is a huge topic area of which I don't have much experience, but a number of the folks that were involved in the research that we were performing in the early days do have clinical psychology PhDs. One of them was a very interesting guy by the name of Eric Shaw, who's still in the community today, and he spent a good 20 years at CIA, and he's now a private researcher. And he came up with a technology called Warm Touch. And what Warm Touch did was it takes the idea of linguistics analysis and automates it in a way in which we can use it to identify potential future adversarial acts from an individual within a large company. So the example that he always gave me was if you were married and you're asking your wife to call in the kids for dinner, there's three ways that you could do that. You could say, darling, can you call Jane and Jim in for dinner? Or darling, can you call the kids in for dinner? Or darling, can you call those kids in for dinner? That's three variant levels of hostility towards your children that you're probably not thinking about at the time. But it exemplifies how we can spot things like that through behavioral and language analysis to identify potential future adversarial efforts against an organization. And he calls this Warm Touch. And very similarly to the matrices that we just described, he came up with a similar mechanism that basically sits on mail servers and spots potential future aggression towards an individual that's the subject of a conversation, the person that the email's to, or any potential anxiety that the individual may be feeling. And in actual fact, has used the technology very successfully in, I think, 1999, 2000, somewhere around then. A Russian national tried to extort Michael Bloomberg for $20,000, I think it was. And what happened is they were able to email back and forth with this guy, and as most of you probably know, the US doesn't have an extradition agreement with Russia. So they had to find some way to get him to the UK. And the way that they did this was to eventually make him an offer, but they waited to a point where they were able to observe that his anxiety levels were at a certain level, and that he would be more amenable to an offer to fly to London, where perhaps he was aware that he may get extradited, and they caught the guy, and it was very successful. So there are some good use cases today of how we can adapt certain non-obvious signal information like that to build models on the adversary's mindset, which we can use for various purposes. So we touched on a few areas previously, but we're going to go into some more depth into those now. And there are various mechanisms that we can use today to perform analysis of attacks without automation, using a slightly modified version of what we as analysts do already. So we mentioned earlier exploit payload analysis, looking for known tool markings. Any of you that were in Greg's talk earlier, he spoke a lot about different tool markings and different compiler markings that you'll find within binaries. And actually Greg's tool that he's released will give you a list of the various markings that a compiler embeds into its code. Normally requires a manual effort to identify, but as Greg's shown, there are ways to automate that process. You'd be shocked at the amount of information that you'll find in binary images if you look hard, especially with lower end attacks. Everything from email addresses, references to MySpace pages, usernames and things like PDB debug strings, and so forth. So there's a lot of static information that often gets compiled into binaries as well that we can draw upon without having to develop too many more tools. Exploit analysis is something that I think in the incident response space we don't really do enough of. And the reason for that is exploits, there's a lot of work often that goes into an exploit when it's embedded within a piece of malware in order to modify it so it works better within that malware framework. So we're not talking copy and paste here from Millworm. There's a lot of effort that often goes into ensuring that that exploit is going to be successful based on the malware framework that it's now a part of. So improve reliability, specific targeting against different host operating system environments. And what a lot of this allows us to do is to create an automated framework, and actually this is something that I'm currently working on building into the tool that I'm going to release, is to compare exploit payloads with knowledge bases of, with a knowledge base of public exploits. So basically we can very quickly determine if a modification has been made to this exploit or not, which immediately tells us whether the malware was written by an adversary that has the ability to make modifications in that manner, and then perhaps flag that malware as something that we want to look at more closely to see exactly what those modifications were and tell us a lot more about the skill set of the adversary. A really good example of this is the ANI exploit a few years ago. This was a buffer overflow in Microsoft's animated cursor file format, and it was worked into a piece of malware. And what happened is 5 years before that, or maybe it was 4 years, there was another vulnerability in exactly the same file format, and everyone deployed IPS IDS signatures. And so what happened was, all of a sudden, there was this ANI exploit, very, very robust, but the 5-year-old IPS IDS signatures, it just so happened that they blocked the new attack as well. So what the malware authors did in this case is they were able to modify the exploit payload to get around these IPSs while still exploiting the vulnerability effectively. So that shows not only a significant level of skill that they were able to make those modifications successfully, but the fact that they did enough research to identify that their malware was going to get blocked by those IDS signatures ahead of time before releasing the malware. So reliability and performance is huge in the automated exploitation space. The quote I've got here: crashes and loose slips sink ships. The last thing you want happening if you've just spent a lot of money or spent a lot of time researching a new vulnerability that's not fixed by the vendor is for it causing crashes all over the internet, which are automatically getting reported to Microsoft so they can go and fix the bug. So reliability and performance is something that these guys look at very, very closely, and they'll focus on how they can improve the performance of the code. So improve shellcode that may involve repatching of memory to ensure that the process remains stable post-exploitation. A good example of this is repairing of corrupted heaps. It's pretty common hat these days that after exploiting a heap condition, you'll call create heap to rewrite the heap area and allow the process to continue executing. But there are various technologies like that that we can observe that attackers may have modified their exploit to use to ensure that the system stays up. The program, whether it be a web browser or whether it be an RPC service, continues running and ultimately reaches the goal of the attacker that they now have the access to the system and no one's found out that they've been attacked, hopefully. Overhead is also a big consideration. A lot of the exploits for browsers that you'll see today, especially for those against ActiveX controls, a lot of those bugs basically involve referencing of uninitialized memory space. And what a lot of the attacks do is they'll create huge heap areas by using lots of JavaScript in a kind of a heap spray fashion. It'll allocate a lot of memory, and then eventually when you trigger what would have been an uninitialized memory reference, you'll hit your shellcode, hopefully. But the downside to that is, I don't know if you guys all use Firefox, but I do, and it already uses 200 megs of memory already. So, if this thing's using 2 gigs of memory because someone's done a huge heap spray, I'm going to be able to notice that. So, another thing that a lot of malware authors will do is they'll do a lot of research into the exploits to make them more reliable. So there's not going to be those other telltale signs of potential exploitation. And all of these, as we mentioned, mount to continued target process execution and the system remaining up. Another thing that we can often look at is also what is the nature of failure. Often a malware author will write a piece of code so that if they don't think they can compromise a certain system, they just won't attempt to break into that system. And that comes back to what we mentioned earlier, the perceived probability of success given attempt accessing a system. But in cases where the exploitation attempt has gone forward, is the exploit aware of any cleanup that might be necessary? Any of you that have caused crashes in Java will know that it dumps a nasty HS error log on the desktop, which is pretty much a red flag that someone's tried to own you. System application level log files are also very important on Windows, especially exploitation against Windows services. You'll find errors in the Microsoft application system and security logs that might be indicators of exploitation. And we don't see a lot of malware for Unix, but in that environment, core files are obviously very important to clean up. We mentioned being able to tune out attacks that are inappropriate earlier, and this again comes back to looking at the exploit and looking at what reconnaissance the exploit performed in terms of identifying the target operating system, language packs, and so forth. And ensuring that the exploit is applicable for that given operating system. So all of these things tell us a lot about the degree of forethought that the attacker placed into writing that malware to ensure that they would be successful. We mentioned ASLR and DEP. It's very difficult these days to get reliable exploitation against systems using hardware DEP and ASLR. With the exception of corner cases like application-specific exploitation, like against Flash using their just-in-time compiler technique. But a lot of malware these days will not attack certain platforms where there's a high probability that these anti-exploitation technologies may be in place. And again, if we're able to determine that a piece of malware does that, that tells us a lot of, about the forethought of the adversary in terms of not wanting to be caught. So these days there's also a lot of attention towards zero-day exploits, and a lot of folks really forget about the fact that old vulnerabilities are still very effective in many cases. A very novice reaction in the analysis world is to assume that anything except for a zero-day means that the adversaries are low-end or low-end in nature. Old attacks are often reworked to be very effective, to be a lot more reliable than the public exploit code that may have been released. There's a lot of cases where previous vulnerabilities may have been released and people may have thought that it wasn't really exploitable, but Microsoft may have fixed it already. So people may have deprioritized remediation of that issue, especially in big data center environments. Those kinds of considerations are always come into play. So it doesn't necessarily mean that they're a low-end adversary, and this is a great example of that. This is if my system will let me display the slide. Well, does anyone know what this is? There you go. So what this is a letter from a military employee in the Asia-Pacific Rim, and it's an email to a Booz Allen employee who is a project manager for a multi-role aircraft project. And basically what the email is it's an order for a multi-role aircraft, and it's very, very detailed. I mean, you have to do a lot of research to get all of the details that they had in this email. And attached to that was an exploit for a 2-year-old Microsoft Access vulnerability. Everyone knew about it. There were IDS signatures for it. And generally, it's, I run a pen test team, and it's not something I necessarily would have even tried. Yet, this adversary that spent so long finding out all of these details about what an order for a fighter jet looks like, decided that this is the exploit that they were going to use. So there's a lot more that you have to look at than just the exploit itself in terms of out-of-band information and preparation for an attack. And in this case, it demonstrates a lot of preparation on the part of the adversary in spite of the fact that they were using an exploit that at the time was 2 years old. Okay, so switching gears again, there are a number of other methodologies that we can use today which are commonly available to provide lineage between different exploits and code bases and malware and so forth. Isomorphism is something that's been studied in the security space, as far as I know, from around 2004, 2005. Isomorphism basically comes from the Greek shape and same, and what it's really saying is we're studying the same shape between different objects. And actually the word comes from the abstract algebra domain. But it's now used in security to really help us identify relationships between different code samples. And there are various ways that we can perform isomorphism, and these are just a handful of examples. This isn't an exhaustive list. Small prime product basically involves assigning a unique prime number to each opcode within a function. What you then do is add up the opcodes, and then that then gives you a sum of that function. And the neat thing about that is it's resistant to reordering of instructions. So if it gets compiled or someone's trying to be sneaky, it allows you to still have the same large prime number. And you may not necessarily want to assign a prime number to every opcode. You may just want to assign one to calls, to API calls, for example. API call structure analysis is another very common method which is used today. If you look at Halvar's tool, VX class, and BinDiff, I believe they use all of these methodologies to achieve lineage between different pieces of malware. There's an example here on the right of the screen where we have two programs, very basic example, but you've got two programs which are making a call to, I think that's regsec key, reg key, query value, I can't see on my screen. Anyway, it's basically two registry API calls with a message box A in the middle of them in the first program. And in the second program, we've got the same functionality without the message box. And you would get a lot of false positives if you use this as a basis for analysis across a lot of programs because it's a very simple profile, but it demonstrates on a basic level how API call structure analysis functions. Function checksumming is very commonly used. MD5 is a common algorithm for this function. And also tracking of variables and constants across different programs where a variable has been defined in a specific function, or even better, a group of variables are being defined as static constants. We can use those variables to identify similar functions in different programs which use those same static variables, therefore increasing the chances that this code has been borrowed or is exactly the same code between different samples of malware. So some further reading if this is an area that interests you. There's a very good paper from, I'm not going to pretend to pronounce their names, but it'll be on the conference CD. And they produced a paper called The Static Birthmark of Executables. And These guys were looking at this for actually the purposes of piracy analysis, and what they wanted to do was to try and determine through API call structure analysis if we can tell if a piece of commercial software is potentially being created from stolen code from another company but using binary images alone. And what they've done is, in their white paper, you'll see all kinds of statistics that they ran on FTP clients that show similarities based on API call structures between similar software. It's pretty cool stuff, and it's been demonstrated to be effective. Halvar, as we mentioned earlier, both his BinDiff tool and VX class help create lineage between malware samples through identifying similar areas of functionality. And there's a number of others in this space, so apologies if anyone's in the crowd and you've written about this. I unfortunately don't have time to go through everyone. Okay, so how can we use this for attribution? Well, the obvious use case is through reuse of code functions. So this is particularly useful for closed source projects where we don't necessarily have access to the source code, where we're pretty sure that the malware is not based off of any kind of commercially available malware kit such as Zeus. And it's very good for tracking the progression of malware and related malware as people further develop malware. You know, most of the malware that we see out there on the internet today are derived from stuff that we already know about. So through being able to track this lineage and spot individual cases where we think the code is completely unique, it really helps us narrow down our efforts in terms of performing more manual analysis. A lot of malware, though, as we mentioned, is based off of kits like Zeus, so it has limited application in that space. You know, if we see two pieces of malware on the internet that are both based off of Zeus, even if they're different versions, they may be different people, they may be the same person. All that really tells us that there's two people on the internet that have both bought the Zeus framework. So that it doesn't help a lot in cases where we're dealing with something like the Zeus platform. Something that I started looking at pretty heavily is how we can perform analysis of the quality of code. And as far as I know, this hasn't been used in the past for analysis of malware. I'm happy to be wrong, though, if anyone knows otherwise. But there are a few examples here of things that we can potentially observe to try and tell us something about the skills of the programmer. The first is nested statements. Anyone that's tried to write C will know that creating heavily nested conditional statements and loops is something that every novice programmer does. Some nesting is unavoidable in a complicated program, but through analysis of heavy levels of nesting, we can potentially determine something about the skill level of the author, and we have some statistics on that in a few slides' time. Things like unclosed files, file handles are often an indicator of a sloppy programmer. Memory leaks, almost every program has some of them, but an excessive level of memory leaks, again, is another indicator potentially of a sloppy programming effort. Redundant functions, multiple functions that get called but replicate each other's functionality is something that, again, may tell us that the programmer has written the malware through maybe patching lots of different pieces of code together from lots of different places and hasn't really looked at the individual functionality and stripping out the redundant functions there. And that's something that we could potentially automate through the use of API call analysis to determine the functionality of a given piece of code and therefore identifying redundant areas of code within that program that perform similar functions. And debug strings being present, again, this is something that I think Greg mentioned this morning, is another thing that we can use, number one, to potentially attribute us to a given individual, but also shows us that the individual didn't have an awareness that he or she was compiling these debug strings into their code, again, which may tell us something about the level of skill that they have. So here's an example of a nested conditional, which can be easy to spot with the naked eye. But in a second, we're going to have a look at how we can automate identification of similar nested statements. As we mentioned, PDB symbols can often tell us, lead us to the identity of an individual. There are numerous cases where I've spotted an individual's username or even their real name, where their Windows username was firstname.lastname in the PDB file, and they just compiled it into the program, not realizing that that reference was there. It can also tell us things about like the operating system that they're using. For example, if they're storing, if you're using Microsoft Visual Studio, the default location for all your projects is going to be My Documents, Visual Studio, 2010, 2009, whatever. And that's therefore going to have either C users or C documents and settings, which will tell us whether you're using XP versus 7 based on those directory structures. So there's all kinds of neat stuff that we can pull out of debug symbols in the code, in addition to it telling us that they didn't really know what they were doing for leaving them there in the first place. So here's an example of Stuxnet, which actually did have a PDB symbol left in it. However, I don't know how well everyone can read that. It isn't really anything that gives us much data. And if you do a little research into the PDB string, you'll see that, and this is one for all of the conspiracy theorists out there that like speculating a little. Myrtus is a botanical reference, and guava is actually a plant which is in that botanical family. I'm not a botanist, I just did some Googling here. And so it turns out that there's a whole bunch of plants which are in this family. They start off at myrtle, clove, guava, allspice, and the final one is eucalyptus. So the fact that they've left this there, most analysis of Stuxnet, anyone that you talk to will probably tell you that they were relatively skilled. The fact that it exploited a zero-day vulnerability in link files tells us something. So perhaps they're trying to tell us something through this debug string, that there are more variants to come, and perhaps the last variant is going to be eucalyptus, which, by the way, is the plant that was commonly attributed to being the burning bush in Exodus. So maybe the last version is going to be super destructive, who knows. Okay, so I'm going to talk about automation for a little while. So automation is really, really important for scale. Anyone that's run any kind of incident response group analysis organization will tell you that one of the big problems is the volume of information out there, the volume of stuff that needs analyzing far outweighs the number of skilled reverse engineers which are available to most organizations. So some level of automation is very, very important to help us scale that response capability. So too much badness, not enough analysts. And those analyst times are probably better spent on edge cases, on things that we can identify are really of interest to us, rather than repeating the same 5 boring procedures again and again and again just to identify that something is derived from something that we already know about and therefore isn't of any interest to us. So one of the first examples of a technology that can help us with that is isomorphic analysis. We already discussed that, being able to create lineage between what we know about and what might have changed within that program, and then just performing analysis of the change parts. And then cataloging of those identifications and markings so that when we see them in the future, we don't have to manually go and look at a database of tool markings that we know about and compare that to the target that we're analyzing, that can happen in an automated fashion. So Black Axon is a work-in-progress tool which I'm posting a link for at the end of the presentation and will be posted after the conference. It's been designed as a proof of concept just to demonstrate how some of these various components can be automated. It's basically an IDA plugin that's using debugger breakpoints and some static analysis to tell you various things about the binary. And because of that, it does mean that malware that has any kind of debugger detection right now can detect it. There are obviously some things that you can do to prevent being seen, such as catching the is debugged API call and making that return in a certain way. But right now, out of the box, you're going to get seen. One of the important concepts of this, though, is that the user sets the rules. I'm a strong believer that different adversaries are interested in different, or other different end users, sorry, are interested in being able to identify different attributes in different malware. So for example, a defense intelligence agency might be more interested in spotting certain attributes in malware that they know are associated with an organization they're interested in, such as a Chinese nation-state sponsored organization. A bank may be interested in spotting traits which are more commonly associated with organized crime and so forth. So it's basically an XML-driven model that allows you to create your own flags, things to look for that you're interested in, and add your own weighting around those, and add your own definitions of how important those things are to you to look for. And so I was originally going to do a live demo, but I think that lots of little text on screens, unless you're popping shells and everyone claps, are completely boring. So for those of you that like little text on the screen, this is an example of the plugin running. What it's basically doing is performing analysis, looking for nested loops within Stuxnet. And there's an example up there of a return from a nested statement. But this is what I think is really cool. I did some analysis using the plugin of various commercially written software against various malware, and this is what we came up with. The higher the score, the less nested statements we found. So basically you have calc.exe to begin with. Secondly, you've got a control which I wrote, which was just some C that has heavy levels of nesting in it. You then got netcat, Stuxnet dropper, Firefox, new war malware, NIMDA, and configure. Now, this doesn't necessarily immediately tell us the skills of each of the individuals that wrote these, because obviously in cases of things like Firefox, multiple people are involved in that process. But it's one metric which we can start to use. It tells us a little more about the adversary and starting to read between the lines in telling us more than just, well, this piece of malware modifies your registry keys, great. You know, it starts giving us more information that we can start building on to, going back to the analogy I used earlier, tell us the kind of firearm maybe that was used to shoot the bullet rather than just that the guy was shot. The other thing that it does is allows you to define chains of API calls. So what we're looking to do here is not just identify what a particular piece of malware does, but how it implements that. So in the first case here, this is an example of persistence where we have two techniques for injecting a DLL into processes. So in the first case, and the first one is very commonly used, configure uses this, where we basically get a list of processes through using the create tool help snapshot. Then we use we get the list of the first process and then walk the tree and then open the process and write to the memory. In the second case, we have a separate example where a piece of malware creates a new process and creates it in a suspended shape, which I think is the sixth parameter to create process. What it then does is virtual alloc, which creates some memory within that process space, and then we then write to the memory area, which injects our DLL. So these are two different techniques which, similarly to the application exploitation matrix that we looked at earlier, we can use to score not just what the malware does, but the merits of the techniques that they use to implement that functionality. There's a second example here where we, again, these are very basic, but where we have some update functionality within the code. And in the first case here, we have actually an example from configure where we have URL download file. It performs a read, then an XOR to decrypt that file, and then it creates process. So we have evidence here of an encrypted update functionality, which we can use as a signature. On the second hand, we have just simply using URL download file and then create process. So it's unlikely that this is going to be an encrypted update. Again, this is something that we can use to score malware. And one of the things that I'm going to be working on over the next month is publishing more signatures like this that we can use to start profiling the techniques and modus operandi that are used by an adversary for implementation of a certain piece of malware. So one of the things I'm unlikely to do for a while, if ever, unless someone pays me full time to do it, is develop this as more of a commercial product. And the way that you might do that is using something like detours hooks or kernel hooks to identify the hit points that you want, the calls to the API functions. And the reason that you do it this way is basically to allow you to sit lower in the operating system, so you're less likely to be detected by the malware. And through using a mechanism like this, you could potentially deploy the software on a lot of nodes across a bunch of workstations and then look for certain behaviors in that manner. My PC wants me to finish my presentation, apparently. Okay, well, so digital evidence forgery. So it's obviously always a possibility that folks may try and forge. Let's, all right, there we go. It stayed. So one of the things that people always say when I'm talking to them about this as well, people can forge data within binaries to make you think that they're a novice and they're not really, and so forth. Well, it's obviously always a possibility, but the key thing about forgery is that you've got to know what to forge. So if you're an intelligence agency, you're going to be building up your own set of analytics and models based on what you're really looking for. And unless the adversary has knowledge of that, it's going to be very difficult to perform any kind of forgery to throw you off. The second part of that is if we're looking at how well the code was written, the benefits of forging inappropriate programming practices may offset the return on investment you're getting from throwing someone off in the first place. For example, putting lots of memory leaks into your program probably doesn't help anyone. It may tell us that you're not a very good programmer, but at the same time it may reduce the reliability of your code because you're leaking memory all over your target operating systems. And so there are obviously times when code analysis can fail, and we don't have a lot of time left, and I want to get some questions, so we'll go through these quickly. It's always important to have other out-of-band data, even if you're confident in your technical analysis, to try and help corroborate what we already believe to be true. So things like command and control channel host correlation between multiple pieces of malware. If we can correlate that one group use the same CNC hosts, maybe in the same subnet or the same ISP, that may help us further identify that there's a link between two groups that we already think might exist, maybe through isomorphic analysis. Check-in server identification, similar to CNC hosts, but check-in hosts are basically where the malware first connect to say here I am. And then post-incident analytics, like using similar methodologies to look at any post-compromise tools that may have been deposited on the file system of the compromised machine, looking at what data was exfiltrated and correlating that with similar types of data that may have been exfiltrated from other attacks that you may also think are linked, and analysis of any other secondary targets that were attacked during the compromise. There are various tools that exist out there that can help us with this process. Plantier, Maltego. I know Greg detailed a lot of this very heavily in his presentation. And good old IRC forums and chat forums often surprisingly useful still these days in terms of creating relationships between individuals and groups where we're trying to observe perhaps a link between two organized crime groups that we may think may be sharing code with each other or may even be the same members in different groups. So the Register ran an article on this presentation at the end of last week, and there's a few there's a few points which I wanted to touch on. And the first was that when folks find out that not all of these attacks that we're seeing on the internet aren't really the work of nation-state sponsors, then all our budgets will get cut. Well, my response to that was really that we need more money to build tools like this so that we can identify the attacks that really matter and toss out the ones that we're not so interested in. And we've got 10 minutes, so actually I'm going to skip to questions in a sec. The tool Blackaxon is available from Google Code /Blackaxon. Blackaxon, beg my pardon. Anyone that wants to contribute or has feedback, more than welcome. It'll remain a proof of concept just to help document various data points and analysis methodologies. It's all GPL, so if you want to take it and build your own code from that, you're more than welcome. And with that, we'll move to questions.
concerned about the first part of your presentation where you just sort of glossed over and sort of minimized the value of personal attribution,
Sure.
such as identifying and enumerating real names behind handles, real link relationships, jobs, locations,
Sure.
communication methods. I think that in order to deter and strategically dissuade a lot of these activities, a intense amount of clear focus on certain individual actors and groups would have a destabilizing
Right.
and chaotic impact on the operations.
I completely agree with you, and that's why I had the point about deterrence and law enforcement in there. And certainly, in attribution at the individual level is very important, but often a methodology like this, in terms of defining groups and linkages between groups, is often a first step to getting you to that end goal of identifying individuals within that group environment. So I think there's a lot of focus today on finding individuals, and certainly law enforcement agencies have many, many more capabilities available to them than just looking at the malware that they do use to try and pinpoint individuals. My focus was really more on talking about the components that don't get focused on so much, such as the creation of linkage between groups, how code gets shared, which I still believe is something that can ultimately help lead you to the end goal, if that is your end goal, of finding an individual. Yeah. Any more questions? No. Going once, twice. All right. Well, thank you very much.